Hey everyone, and welcome. Today, we're going to tackle one of the most fundamental ideas in all of chemistry, chemical bonding. We're going to break down exactly how and why atoms link up to create literally everything around us. All right, let's get right into it. So let's start with the biggest question of all, right? Why do atoms even bother sticking together? Why can't they just be happy flying solo? Well, the answer, in one simple word, is stability. You see, atoms are kind of like us. They're on a constant search to be as stable and as low energy as possible. So here's the game plan. We'll kick things off with that quest for stability. Then, we'll look at the two main ways atoms get it done, ionic and covalent bonds. After that, we'll see how these bonds create cool 3D shapes, and we'll wrap up with a quick quiz to make sure this all sticks for your exams. First up, let's figure out what stability really means for an atom. And honestly, it all comes down to their electrons. Specifically, the ones on the very outside. There's a super important rule that they all live by. And this right here is the golden rule. It's called the Octet rule, and it's the driving force behind pretty much all of chemical bonding. Atoms want to have a full outer shell with 8 electrons. Now, why 8? Well, because that's what the noble gases have. You know, like neon and argon. They're basically the cool, unbothered celebrities of the periodic table. They're super stable because their outer shells are already perfect, and every other atom wants to be just like them. Now, to help us see what's going on, we use these things called Lewis dot structures. Think of them as super simple blueprints for an atom. You just write the symbol, and then you use dots for the outer electrons. Just look at the difference here. Sodium, with its one lonely dot, its one valence electron, it's super reactive. But argon, it's got that perfect set of 8. Sodium is desperate to get rid of its one dot to be stable, while other atoms are desperate to gain dots to hit that magic number 8. So, what's the first way atoms can get that perfect octet? Well, if you've got one atom that really wants to give away an electron and another that really needs one, they can just make a deal. And this brings us to our first bond type, the ionic bond. An ionic bond is all about giving and taking. No sharing here. One atom, usually a metal, completely transfers an electron to another atom, a nonmetal. This simple act creates ions, atoms that now have a charge. And you know what they say, opposites attract. That intense pull between the new positive and negative ions, well, that's your ionic bond. And the classic example, the poster child for ionic bonding, is sodium and chlorine. Sodium is a metal with just one valence electron. It would be so much happier if it could just ditch that one electron. Then you have chlorine, a nonmetal with 7. Oh, it's so close to a full set. It is incredibly eager to just grab one more. You can already see where this is headed, right? And here's how it all goes down. Sodium gives away its electron, turning into a positive ion, Na+. Chlorine snatches it up, becoming a negative ion, Cl-. And just like that, boom, both atoms now have a stable octet. That powerful positive-negative attraction then snaps them together, forming sodium chloride, which you probably just know as table salt. Need a quick way to remember this for your tests? Just think of ionic as I give you Nick, an electron. It's all about one atom giving and the other taking. It's a silly little trick, but trust me, it works. Okay, but what happens when you have two atoms and they both want to gain electrons? Neither of them is going to give one up. Well, this is where our second type of bond comes in. Instead of giving and taking, these atoms decide to cooperate. They share. And that, my friends, is a covalent bond. The key word here, the most important word, is sharing. Instead of a full transfer, two nonmetal atoms each contribute electrons to a shared pool. These shared pairs of electrons then circle around both atoms, holding them together like glue. Let's take methane, a perfect example of this. You have a carbon atom in the middle with 4 outer electrons, so it needs 4 more. And then you have 4 hydrogen atoms, and they each need just 1 more electron. So what happens? Carbon teams up with all 4 hydrogens. It shares 1 electron with each hydrogen, and each hydrogen shares its electron back with carbon. The result? Everybody's happy. Carbon gets its full octet, and each hydrogen gets its stable pair. It's a win-win. All right. This is a super important slide for your exams, so let's do a quick side-by-side. The biggest difference is what the electrons are doing. In ionic bonds, it's a transfer. In covalent bonds, it's all about sharing. And remember who's involved. Ionic is usually a metal plus a nonmetal. Covalent bonds are between nonmetals only. So, we know how atoms bond, but it gets even cooler.
These bonds don't just exist as flat lines on paper, they create actual complex 3D shapes. But what decides what shape a molecule will be? I mean, think about it. Why is a methane molecule, CH4, a perfect little pyramid shape, a tetrahedron, but a water molecule, H2O, is all bent out of shape? They both have a central atom bonded to other atoms. So what gives? Well, it turns out it's all about the electrons that we don't see in the bonds. The secret is something called VSPR theory. Now that stands for valence shell electron pair repulsion, which sounds really complicated. But the idea behind it is incredibly simple. Electron pairs hate each other. That's it. Since they're all negatively charged, they push each other away. Whether they're in a bond or just sitting on the atom as a lone pair, they will try to get as far apart from each other as physically possible, and that pushing and pulling is what locks a molecule into its final 3D shape. Now check out this table. It really shows you the power of those lone pairs I mentioned. In methane, you have 4 bonding pairs and 0 lone pairs, so they spread out perfectly into that tetrahedral shape. But look at ammonia. It's got 1 lone pair, and that lone pair is extra pushy. It squishes the 3 other bonds together, creating that pyramid shape. Water is even crazier. It has 2 super powerful lone pairs that shove the 2 hydrogen bonds even closer together, giving water its famous bent shape. All right, we have covered a ton of ground. We figured out why atoms bond, the 2 main types, ionic and covalent, and how those bonds lead to 3D shapes. So let's do a quick final summary and then test what we've learned with a few exam questions. Okay, if you only remember 4 things from this whole explainer, make it these 4. 1, atoms bond to get a stable octet. 2, ionic bonds are about transferring electrons. 3, covalent bonds are about sharing electrons. And 4, VSEPR theory says electron repulsion determines a molecule's shape. Got it? Awesome. All right, question 1. Now this question uses the term electronegativity. It's basically a fancy word for how electron greedy an atom is. It generally increases as you go across and up the periodic table. Looking at our choices, oxygen is the farthest to the top right, which makes it the most electron greedy. So the correct answer is B, oxygen. Next one, an element with atomic number 11, that's sodium. And we already know its story, right? It has 1 valence electron. So what does it want to do? Well, it's way easier to just lose that 1 electron than to try and gain 7. And when an atom loses 1 negative electron, it's left with a charge of positive 1. So the correct answer here is A plus 1. And our final question. The central oxygen atom in water starts with 6 valence electrons. It uses 2 of those to make the bonds with the 2 hydrogens. So how many are left over? 6 minus 2 is 4. And since electrons hang out in pairs, those 4 electrons make up 2 lone pairs. So the answer is 2. And remember, it's those 2 lone pairs that give water its signature bent shape. And let's finish with this thought. We know that atoms are more than 99.9% empty space. Yet these invisible forces, these chemical bonds, are strong enough to build mountains, to hold the oceans, and to build you and me. The entire solid world we experience is just held together by these fundamental attractions. It's pretty amazing when you stop to think about it. Thanks for watching.